Now to get a preview of one of this week's carefully crafted symposia, I'm joined by Chair Professor Jonathan King to learn more about the themes behind it. Thank you so much for joining us, Professor King. First, tell us about kinetic stability and what's the overall focus of the symposium?
Now we're at a point in biophysics where we're beginning to bring the basic biochemistry into the question of human disease, human pathology, what's actually going on in the body. And inside the body, proteins are in a very different environment. You know, you think about a muscle, those myosin or tropomyosin or troponin molecules, they're not in solution. They're in some very dynamic interacting state, interacting with small molecules, big molecules. And it turns out if you really want to understand what's happening in the body or what goes wrong in the body, you need to understand the rates or what we call kinetic stability, how fast or how slow processes take place. And that requires a different measurement than just the equilibrium.
What exactly will be covered in the session?
We'll be covering the range of proteins that show this big difference between thermodynamic and kinetic stability. The molecular determinants, what are the interactions, amino acid interactions inside proteins that give it, or features give it this kinetic stability. Its relationship to this very important class of diseases, amyloid diseases, and also that leads to the notion, well, maybe we can prevent the accumulation of some of these most destructive forms of the protein, the amyloid fibrils, by if you understand the pathway by which they form, you might be able to intervene with small molecules.
Which is always the most important,
Yes.
right? Being
Yes.
able to intervene.
Yes.
Can you show us on the screen, please, with some of your own work, how you're looking at the cataract?
Well, here's a diagram of the eye, and in the center there is the lens, which has to be transparent so that light passes through. Lens is a very distinct tissue. It's packed full of a distinct class of proteins called the crystallins. This is true in all lenses of all vertebrates, marine mammals, etc. And I'm going to talk about the gamma crystallins, which are key proteins. And for every person out there who's looking at this slide, you're seeing it through a population of crystalline molecules that was synthesized when you were in your mother's womb. So these proteins have to remain folded and stable all your life. And if they don't, if they slightly unfold and those things stick together to form a very stable aggregated state, then you get cataracts. We've now been able to identify, well, exactly what are the forms of damage that lead to this state, at least for damage due to ultraviolet light, which is one of the major etiological causes of cataract in humans and in animals.
How do you think your work is going to help people ultimately?
If you have millions of people getting cataract surgery, the complications are in hundreds of thousands. Many people are not able to get cataract surgery, and so we feel that if you really understand this pathway, as we're coming to do, you ought to be able to interfere with it with small molecules, which could be applied as eye drops, and ought to be a very effective way. The first such small molecules are coming into clinical trials. So we hope for humans in the years to come, it'll be possible to slow down or prevent cataracts in older people.
Well, so much to look forward to for so many of us who suffer from this. We don't even know it, but we do. Thank you so much for joining us, Professor. Really appreciate it.